I am doing this video because I want to help you out for this next lab. So this next lab is actually, it's a little bit easier than the other previous labs that you had, but I wanted to go through an explanation with you. So by the time that you see this video, it'll be super straightforward and just get to getting all the data. Okay, so first of all, we have to understand what a standing wave is. So a standing wave is a wave that actually transports energy from one place to the other. And under certain conditions, the wave actually bounces back and forth through that particular region, effectively becoming a stationary wave. So we saw it in the experiment that I did yesterday or in the previous class, where we saw the wave, or we saw the string just bouncing back and forth. Now, a standing wave has both nodes and antinodes. So we had a little bit of confusion on what both of them were. So a node is the equilibrium position of the wave. So there's only in this situation, the equilibrium positions is, and let me just put it annotated in red over here. Over here, these are equilibrium positions. However, an antinode are the maximum displacements from its equilibrium position. Therefore, they are up top, over here. Those are antinodes. Okay, so now we understand a little bit of a gist of the standing wave. We also have to understand what a wavelength is. So a wavelength is the actual example of a point that has a very similar point on the other side. So if we erase this, what I'm talking about is this is one point that we start here, and then this is a very similar point right here. This has now a full wavelength. Okay? When we're comparing it with length and wavelength, let's not confuse it, because we have a length right here. So we have our length right here of the string. And I'm getting towards the left. But for a wavelength, it has to complete a full round up and then down. That is a full wavelength. Okay? Now, we also have this situation right here where it's one full wavelength and then one full wavelength and then another full wavelength. So now we're counting for two. Do not misrepresent this as nodes and antinodes. We have that confusion. I confused myself yesterday too. They're just considered modes, or in this situation is the first harmonic, the second harmonic, the third harmonic, and finally the fourth harmonic. Okay? So every time that we complete a full wavelength, we account for the mode. So in this situation, we have two complete wavelengths. In this situation, we have three. So 1, 2, and 3. Finally, for the lab, see, this is what we want you to do for the lab. For the string, we want you to do 4 wavelengths, 4 modes, 4 harmonics. Okay? So this is how you're gonna make sure that your lab is, or at least your strings are showing when you're doing it. This is the equation that you're gonna need for the relationship between the wavelength and the length of the string. Since we're requiring you to do 4 modes, therefore it's gonna be equal to L over 2. Because n is 4, so 2 over 4 is 1 over 2, and you follow the rest. So this is the lab right here. This is a lab setup right here. And if you want to look more into it, you can always check chapter 16.6. This will help you out for your actual theoretical portion. So in chapter 16.6, it actually explains the lab, but I'm going to go through it a little bit here. So the lab setup that we see here shows a string attached to a string vibrator right here. Okay? And that vibrator oscillates the string with an adjustable frequency. So as we saw in Pascal and the other time, you can actually manipulate the frequency here. So I'm sorry, that does not look like a frequency. There we go. Frequency. You can manipulate the frequency using your Pascal. So I'm going to put parenthesis Pascal. Okay? Now, the other end of the string passes along somewhat of a frictionless pulley. So it's not completely frictionless in our actual lab setup. But you can make the assumption, and hint, this would be good for your lab report, that, hey, the pulley here, we can assume that is frictionless. And it is tied to a hanging mass. For this example, it is 2 kilograms. Now, the magnitude of the tension in the string is equal to the weight of the hanging mass. So if we do our PH205 stuff, remember that? Like beautiful stuff that we did in PH205. So we have X, remember X, like that X direction is always in the direction of motion. And we have tension for the pulley, and then we have mass times gravity. So Ft is equal to mass times gravity, or the weight of the tension is equal to mass times gravity, or acceleration due to gravity. Now, the string also has a constant linear density, mass per length, and that is annotated as this, mass per length. Okay, and I'm writing it here for a reason. And we'll talk about the accepted value in a little bit. And that will that will help you determine the speed at which the wave travels down the string. And the speed at which the wave travels down the string is this famous equation that we've seen here, whereas it's the square root of the force of tension over linear density. Okay? Now, in order to identify the accepted value of your setup, then you're going to have to weigh your string, the weight, or find the mass of the string using our scales. And find the length of the string. You find those two things and you'll get your own accepted value. We will not give you an accepted value. You will have to find it on your own. So find the mass of the string and find the length of the string. So I had a little bit of confusion last time that I was explaining this to you. But in actuality, the way that the experiment goes in the lab is that you always have to hit for harmonics. Okay? As I'm circling it right here. 4 harmonics. Meaning that the way that you're going to do this is that you're going to change the mass. The mass will be your independent variable. You're going to change your mass of the string. That will change your tension. But you're always going to have to hit those 4 modes. So after you change the mass of the string, what you're going to do in order to make sure that you continue using, like your string looks exactly like this, you're going to have to change the frequency And your frequency is going to be your dependent variable. Your dependent variable. Therefore, it has nothing to do with the notes. It has nothing to do with the harmonics. You're going to always continue hitting 4 harmonics, 4 notes, like the one that I'm highlighting. And I'm going to highlight it again in red so you understand that it has to look like this. Your string has to look like this. Okay? You're going to change your mass. And as you change your mass, you're going to change your frequency in order to meet your 4 harmonics. Okay? Now, let's go into the linearization of a linearization table. So we spoke a little bit about the velocity of the string. So I'm going to write this down to identify the actual velocity of the string. This is a physics over linear density. Now we find the accepted value, but remember, our goal is to find the actual linear density. So you're going to compare your experimental value with your accepted value. Then we also look that velocity is equal to the wavelength of the string, or the wavelength of what you're seeing, times the frequency. But wavelength is equal to 2L over N, just like we spoke of. And N is equal to 4 because we want 4 modes, right? So we will have the wavelength will always equal to L over 2. Okay? So now what we do is, now that we have identified these equations, what we do is that we have to apply it in such a way that we create a linear relationship. So we don't have velocity, but we can change velocity because we have frequency, which is going to be our dependent variable. And we also have wavelength because we have the length of the string, and we know that we need 4 harmonics. And we know that in order to find the wavelength, we have to divide it by 2. Okay? So we replace it, and we will have L over 2, right? Because this is where the wavelength is, times the frequency equals the square root of the force of tension, which, by the way, the force of tension is also equal to mass times gravity over the linear density. Now, as we spoke of before, we identified that the dependent variable is the frequency. The independent variable is going to be the mass that you change in order to continue to have those 4 nodes. Okay? Now we have to change it into a linear equation. So we have to convert it into something to this effect. Y equals the slope times x. So we're looking at it in such a manner where it's like x, y, and then we create a linear equation. Okay? So y will always be frequency because it's the dependent variable. And then that will equal to the square root of m, because we're looking at here, right? The square root of m. And that's going to be our x times our slope. And let me, in order not to confuse you, I'm going to square root of m. There we go. That's our x right there. And then we write gravity, acceleration due to gravity, the square root of acceleration due to gravity, times 4. And you can do the math. You'll find out why, okay, let me erase this. It's kind of messy. So let me square root, because this is the slope. Gravity, acceleration due to gravity, times 2 squared. And that's going to equal to 4. Remember, you have your 2 right here, so I'm bringing it over into the square root. If you're bringing it over into the square root, what you have to do is you have to double it. Yeah, squared. 2 squared. Okay? And then you're also going to include the line the length squared times the linear density. Because again, I'm bringing the length to the other side to the actual square root, and that's why I'm squaring it. Okay? All right, so now we have our y, our slope, and our x. And if you want, you can verify doing your math if this is correct. Independent quantity, you're always having issues with that. So independent quantity will be the square root of m. It's exactly how it's portrayed in the actual x direction. So when you're doing your linear regression in your Excel spreadsheet, this is going to be the square root, right here, the square root of m. And then for your dependent quantity, it's just going to be f, because f frequency is left by itself. So f over here. Now your objective quantity is going to be your linear density, because that's what we're trying to look for. Your control variables is whatever is inside that slope. So whatever is inside that slope is your gravity, your acceleration due to gravity, and your length. 4 is a constant. It's just a number, so it really doesn't include in the control variable. Acceleration due to gravity and length include also a confidence interval. So do not forget about that confidence interval, because it's gonna help you on your propagation of error. And then finally, write the expression for the slope. So we actually analyze the slope, and the slope is equal to the square root of acceleration due to gravity times 4 over L squared times the linear density. And if you wanted to, now it's saying rearrange your slope, so you solve for the objective formula. So the objective formula is the linear density. So equals, we take that out, and what we have is acceleration due to gravity times 4 over L squared slope squared. Now you can verify these numbers, these equations again. Okay, please do let me know if you find any errors on this. I am just trying to teach you where all this is coming from. Now for the error propagation table. So we are trying to find the objective quantity. The objective formula is this equation right here, G4 over L squared slope squared. Because we have this objective formula, we need to find the variable of G, L, and the slope. All these three have a measured value, and they also have an absolute uncertainty into it. When you do your linear regression, there is an absolute uncertainty. Make sure that you identified the absolute uncertainty for gravity, and make sure that you identify the absolute uncertainty for length. And this one is just basically plug and chug, right? So you're trying to find the actual value for your linear density. So just plug in the values of the acceleration due to gravity, the length of your string, and the slope that you found using your linear regression. Finally, for this one, it is your propagation of error. So I am not going to do this propagation of error. I want you to do it, but I just want to make sure that you understand that what all the things that you require. So you're trying to find the actual absolute uncertainty for the linear density. So you need, it's the other way around. You need the gravity, the acceleration due to gravity. You need the propagation of error for that. Or not the propagation error. You need the absolute uncertainty. So this signifies absolute uncertainty for for gravity, acceleration due to gravity, plus you also need the absolute uncertainty for your length. So make sure that you calculate that, or you not calculate it, but measure that. And finally, you need the absolute uncertainty for your slope. So that has to be included. Slope it right here. And voila. Make sure that you do your partial derivatives on each of these, and make sure that you include the absolute uncertainties for acceleration due to gravity, the length, and the slope. And then make sure that you add your problem, plus or minus. Okay, now I am using the tables, but remember, this is a written document. So you have to write the document and you have to explain this in prose, in words. Okay? All right. I hope this was helpful. Let me know if you need anything else. I'll be here. All right. Take care.